Hello, and welcome to Hot Water Design for Heat Pump Water Heaters in Commercial Kitchens. There will be a speaker icon on every slide which will start playing the voiceover.
The information found in this presentation is a distillation of lessons learned from multiple laboratory, field, and industry characterization studies performed for the commercial food service industry. These lessons have been compiled into a new operator's guide for advanced water heating within the food service industry by a team of energy industry professionals from TRC and Frontier Energy. This document is accessible at the link on this slide and goes into further detail than this presentation. This was made possible with funds from the CalNext program.
This 2023 design guide builds from previous iterations. The first design guide was published in 2010 and was funded by PG&E and the California Energy Commission. The second revision of this design guide was first published in 2021 with funds from SoCalGas. By the end of this presentation, viewers will be able to describe the water and energy savings associated with heat recovery dish machines, understand the benefits of using heat pump water heaters in commercial food service, understand how heat recovery dish machines and heat pump water heaters can make each other cost effective, and understand the design examples for energy efficient hot water systems for quick service and full service restaurants. This presentation and the design guide can both be found at the CaliforniaEnergyWise.com website. This website also has multiple other resources for food service and energy industry professionals. The California EnergyWise website includes directions for energy surveys to help food service operators understand their energy usage, design guides to help facility designers design more energy efficient kitchens, links to upcoming in-person and virtual seminars, as well as recordings from previous seminars, which contain tips on best operating and design practices, as well as results from lab and field studies, instructions on how to participate in Frontier Energy's Try Before You Buy program, which allows food service operators to test drive new cooking equipment, calculators to help compare the energy and cost impacts of different pieces of kitchen equipment, and information about how to access rebates for food service equipment. Section 0, Preamble. Why do we care about hot water systems? Hot water is critically important for commercial food service facilities because it provides most of the sanitation. Hot water is largely the lifeblood of restaurants. Without it, operators cannot clean their hands, wash dishes and equipment, or cook food. Hot water touches virtually every part of a commercial food service facility. Health department regulations basically say that you can't run a restaurant without adequate hot water delivery, basically for fear of getting people sick. Hot water systems are also highly energy intensive. In California, they use 340 megatherms per year, which accounts for about 16% of all commercial gas usage statewide. Hot water systems can also account for as much as half of a commercial food service facility's energy usage. So it's very important for a facility's bottom line as well as for its overall operation. The table on this slide shows the gas use from different facility types in the commercial food service industry. This was measured in a gas-fired DHW system study. Full-service restaurants account for the majority of the overall gas load from commercial food service domestic hot water systems. This is in part due to the prevalence of these facilities and in part due to the hot water load. Quick service restaurants are the next highest segment. The design examples in this presentation cover full service and quick service restaurants because these segments account for 3/4 of the overall load. The utility rates used to calculate values in this presentation are in the table to the right of this slide. The water and wastewater cost is $14.16 per 100 cubic feet. The gas rate is $1.65 per therm, and the electricity rate is 33 cents a kilowatt hour. These rates reflect current California utility rates and projections for 2024. Generally speaking, utility rates are rising and are rising a bit faster than inflation. and they're projected to continue rising a little bit faster than inflation throughout the rest of the decade. Um, Electricity and gas rates have been going up as a general trend over the last 10 to 15 years. And electricity is set to actually outpace gas in terms of how much it's going to increase. This is going to make fuel switching from gas to electricity a little bit more difficult financially going forward. Um, but later in this presentation will show that it still can be cost effective in some cases. Hot water systems are divided into three main parts: hot water delivery and fixtures, distribution systems, and hot water generation. In section 1 of this presentation, we will discuss hot water delivery, points of use, and fixtures. This will include dish machines, pre-rinse spray valves, other pre-rinse operation equipment, hand sinks, and lavatory sinks. Section 2 will cover distribution systems, which is the set of piping that connects water heaters to fixtures. This will include hot water piping, insulation, and recirculation systems and their control systems. Section 3 will cover hot water generation, which will talk about different kinds of water heaters and their various efficiencies, different schemes to increase the uh, overall operating efficiency of these water heaters. And finally, Section 4 will cover design examples in a quick service and a full service restaurant that will bring all of this information together. This table shows industry standard hot water system energy and water intensity for the commercial food service industry. An average quick service restaurant will use about 500 gallons of hot water per day, whereas an average full service restaurant will use around 2,000 gallons of hot water per day. This is largely due to differences in these systems. Quick service restaurants typically will have much smaller systems than full service restaurants, and full service restaurants will typically need to use larger and a larger number of dish machines than a quick service restaurant would. Full service restaurants typically will rely more on in-person dining and reusable dishes rather than quick service restaurants, which can rely more on takeout, which is a large part of the reason that the water uses between these two types of facilities are so different. This has consequences for their overall energy use and their annual utility costs. The natural gas used for a quick service restaurant is about 1,600 therms per year, whereas a full service restaurant will use about 8,400 therms per year. It is assumed for these restaurants that they're using standard efficiency tank type natural gas fed water heaters because these are the most common type of water heater found in the commercial food service industry at the time of this recording. A full service restaurant will also use about 74,000 kilowatt hours per year to feed its dish machine and its recirculation pump. The water and sewer costs follow the water usage, and the natural gas and electricity costs follow the natural gas usage and electricity usage, which leads to an annual utility cost for the quick service restaurant of $6,300 per year, whereas a full service restaurant will use almost 10 times more at $52,000 per year. This is largely due to the difference in water usage, which drives a difference in natural gas usage, and the fact that the full service restaurant has to use a significant amount of electricity as well as natural gas to fuel its system. The savings potential for hot water systems in quick service and full service restaurants is pretty substantial. A best-in-class quick service restaurant will use a high-efficiency gas-type water heater, as well as high-efficient fixtures such as a high-efficiency pre-rinse spray valve and low-flow aerators. A best-in-class full-service restaurant will use efficient fixtures and will use a heat recovery dish machine, which will lower the load on its upgraded efficiency water heater. These changes lead to annual savings over conventional of about $1,800 per year for the quick service restaurant and about $11,000 a year for the full service restaurant. These savings are pretty substantial and can help to justify the cost of replacing equipment even in the middle of its service life. The design path for savings will help designers engineer systems that can achieve the savings potentials that are listed on the previous slide. The first step is to specify efficient hot water equipment. This step will lower the total amount of hot water demand, which will have many design implications as designers move from the fixture all the way back to the water heater. The next step is to build an efficient distribution system and to optimize the control of the recirculation loop. This will further reduce the energy demand on the water heater. Once these are achieved, the designer should specify a high-efficiency water heater. There are multiple examples of high-efficiency water heaters listed later in this presentation and in the design guide. The last step is to commission and develop a maintenance and equipment replacement plan. Once the system is actually designed, it is imperative to commission the system as it is actually designed and then to maintain that system so that it operates as the designer intended it to. It is also important to have an equipment replacement plan so that the operator can make good decisions about what to do when pieces of equipment invariably burn out. Section 1. Fixtures and dish machines.
Specifying efficient fixtures is an important design step for many reasons. The first is that efficient fixtures limit the hot water demand, which reduces both water and energy consumption. The second, and most important from a design perspective, is that reducing hot water demand affects every other part of the system. Pipe diameters, both for branches and for the main recirculation loop, can be smaller if low water use fixtures are used. Hot water demand also plays a role in sizing the water heater. A system with efficient fixtures can have a smaller water heater, which can help reduce the first cost of the system. Most of the hot water demand in a commercial kitchen comes from the dish room because this is where most of the critical sanitation tasks happen. The data from this graph comes from a field study where each hot water fixture at a full-service restaurant was monitored. The study showed that almost 3/4 of the hot water consumption occurred in the dish room, and almost half was consumed by the dish machine. The dish machine is typically the most hot water intensive fixture on a hot water system, so selecting an efficient dish machine is one of the most important tasks for hot water system design. There are 4 main classes of dish machine commonly found in commercial food service facilities. Larger facilities typically require larger dish machines as they can wash larger volumes of dishes. The smallest dish machine is an under-counter machine, typically found at bars and cafes. They are also found in front-of-house bars in larger full-service restaurants. Under-counter dish machines are by far the most common type of dish machine. Upright door-type machines can wash between 45 and 60 racks of dishes per hour and are commonly the main sanitation workhorse of a full-service restaurant. Rack conveyor dish machines use a conveyor to feed racks of dishes through the washing chamber and can wash up to 90 racks of dishes per hour. They are commonly found in very large full-service restaurants and cafeterias. The largest class of dish machine is a flight-type machine named for its use in airport commissaries. They use a conveyor with plastic fingers to feed dishes through the washing cavity and are commonly found in large institutional facilities such as university and prison cafeterias. To size a dish machine, a designer needs to know the estimated dish throughput of the facility. A common design misstep is using an oversized dish machine for the actual load. This can cause lower system efficiency and water and energy waste. This table lists the energy and water use of small dish machines. It compares the manufacturer's rating to the real-world as-measured water and energy usage for under-counter and door-type dish machines found in conventional, Energy Star, and best-in-class efficiency classes. Under-counter dish machines typically have water uses rated between 0.6 and 0.8 gallons per rack of dishes washed. In the field, they're typically found to consume between 0.7 and 2.5 gallons per rack. This is a common feature among dish machines, that they'll use more water in the field than the manufacturer's rating. This is usually due to maintenance concerns, as most dish machines tend to use more water as they age in the field over time. Door types are usually rated between 0.6 gallons per rack and 1.0 gallons per rack. In the field, they're usually found to consume between 0.75 gallons per rack and 1.4 gallons per rack. This table lists the energy and water use of large dish machines. The data in this table is normalized to a per hour of rinse use metric rather than a per rack metric because that's much easier to measure in both the lab and the field. It also compares the manufacturer's rating to the real world as measured energy and water usage for rack conveyor and flight type conveyor dish machines. These machines typically use much more water than their door type or under counter counterparts. One of the most important emerging technologies for efficient dish room design is the exhaust heat recovery dish machine. These machines use a heat exchanger to capture the heat generated by the dishwashing process, which is normally lost when the waste steam goes through the exhaust hood. The energy from this steam preheats incoming cold water. The preheated water is then sent through a booster heater to reach its final rinse temperature. Door type and under counter heat recovery dish machines can preheat incoming cold water to between 110 and 130 degrees before reaching the booster heater. They have been shown to use the same amount of electricity as their conventional high temperature dish machine counterparts in the field. However, heat recovery dish machines consume far less hot water. Some don't even have a hot water connection. They therefore present sizable hot water and energy savings at the water heater. They have also been shown to project less heat to the dish room space, therefore saving air conditioning money and contributing to a more thermally comfortable working environment. They also require less or no ventilation, saving energy at the exhaust fan. This is an important point for HVAC designers because in some cases, dish rooms can be designed without an exhaust fan altogether when using an exhaust heat recovery ventless dish machine.
This table shows the operating costs of various high-temperature rinse door-type dish machines. This data comes from a field study where a baseline machine was replaced, first with an Energy Star dish machine and then with an advanced exhaust air heat recovery dish machine to measure the cost savings of the replacement machines. The baseline machine used about $23,000 per year between its water and electricity costs and the gas consumption of the water heater. The exhaust air heat recovery machine saved about $7,000 per year even though it washed the same number of dishes per day. The heat recovery machine used roughly the same electricity as the baseline machine, so its savings were attributable to its much lower water usage and the fact that it didn't consume gas because it didn't have a hot water connection.
Many manufacturers produce an exhaust air heat recovery dish machine and sell them in the US. Many manufacturers also make cold water feed only machines available in door type and under counter models.
If the hot water demand is smaller through the use of efficient fixtures and heat recovery dish machines, pipe diameters can also be smaller. This helps to save energy everywhere in the distribution system because there is less pipe surface area for heat loss. It also improves overall hot water delivery performance. These graphs show wait times for various lengths of various diameter pipes for 1/2 GPM hand sinks. A common health department rule of thumb is that hot water should be delivered at hand sinks in less than 10 seconds, which is where the red dashed line is placed. For hand sinks, it is generally a best practice to use 5 feet or less of 1/2 inch diameter copper pipe to preserve 10-second wait time. 3/8 inch piping would allow for lower wait times for hand sinks, but due to outdated sizing guidelines that don't take half GPM hand sinks into account, this is not currently allowed. The common practice is to feed hand sinks with 3/4 inch diameter piping, but this means that branches to hand sinks need to be less than 2 feet long to preserve 10-second wait times. Now that the hot water load has been minimized by selecting efficient fixtures, a more efficient distribution system can be designed. Section 2. Distribution Systems.
The distribution system design best practices listed here are all designed to reduce the total amount of hot water distribution system piping. This will reduce energy waste through the distribution system. Mirroring men's and women's restrooms is an obvious place to start because it will reduce the number of branches coming off of the main recirculation loop. Locating the dish room on a wall opposite the front of house and placing any auxiliary bar fixtures or restrooms on the other side of the dish room wall is another way to reduce the total amount of piping. Centrally locating the utility room and locating the utility room near major points of use is a good rule of thumb. Locating all of the fixtures close to each other will reduce the number of branches that you need to have off of the main recirculation loop. There are two types of conventional distribution systems commonly found in commercial food service facilities. The first is the simple distribution system, which connects a main hot water trunk to the water heater, then branches off to each fixture. The main benefit of this system is that it's easy to design and install, but the main drawback is that there are usually significant delivery problems, especially long wait times at hand sinks. California building codes state that if there are fixtures located more than 60 feet away from the mechanical room, simple distribution systems are not allowed. They are therefore usually found in quick service and very small full-service restaurants. One common configuration is to run two distribution lines, a 140-degree sanitation line and a 100 to 120-degree hand sink line. This greatly increases energy waste because of all the extra piping. The other type of conventional distribution is a continuous recirculation system, which uses a pump to keep a recirculation loop near the water heater's set point temperature. This improves hot water delivery because instead of having to draw water through the whole system, each fixture only has to clear the water in its branch before it sees hot water. This method does not always ensure that hot water makes it to the faucet. Hand sinks still have delivery problems with continuous recirculation systems. High operating costs are incurred in a typical full-service restaurant because hot sanitation water circulates all the time, constantly losing heat to the surroundings. One method for reducing the energy waste from continuous recirculation systems is to install a demand circulation controller. These controllers use occupancy sensors, temperature sensors, and timers to ensure that the recirculation pump only runs when hot water is needed. They can reduce the pump runtime from 24 hours per day to less than 2. This reduces recirculation system pipe heat losses, saves pump energy, and improves water heater operating efficiency. It is especially effective for systems that use a condensing water heater because they can help preserve tank temperature stratification. An emerging distribution strategy is distributed generation. These systems use a main recirculation loop to feed the fixtures close to the mechanical room and use small point-of-use heaters to feed hot water to fixtures that are far away. These point-of-use fixtures are usually electric so that they don't need to be vented. This greatly reduces the amount of hot water piping. In the example shown on this slide, a heat recovery dish machine is also used, which means that the main recirculation loop can run at a lower temperature than 140 degrees, thus saving additional energy on the main loop. Pipe insulation is an obvious and easy energy-saving technology for hot water systems. Designers should specify insulation on all hot water supply, return, and branch lines to make sure that the minimum amount of energy is lost from the piping system to the ambient surroundings. In addition to being a very effective energy-saving technology, pipe insulation is actually called out for hot water systems in California's Title 24. This table shows the insulation conductivity and the minimum pipe insulation required per nominal pipe diameter for different temperatures of fluids. Pipe insulation is commonly specified for hot water systems, but in practice, it is often poorly installed if it is installed at all. Pipe insulation should be installed on the cold water pipe leading to the expansion tank, as well as on all of the other hot water piping. Pipe supports should be installed on the outsides of pipes because if installed on the pipe's surface, they can act as thermal bridges or fins which can rapidly bleed heat to their surroundings. T's and turns are also commonly uninsulated, but can be easily insulated according to the schematic at the bottom left of this slide, which shows how to create a notched T and a metered elbow.
Master mixing valves can increase the effective hot water storage capacity because they allow for the water heater to operate at temperatures much higher than the desired system set point. The MMV tempers this overheated water with cold water to produce the desired set point temperature in the supply loop. This is very important for water heater sizing, especially for heat pump water heaters, which typically have slow recovery rates and depend on storage volume to provide adequate performance. Running the water heater at a higher temperature can improve tank stratification when used with a master mixing valve. Instead of allowing 100% of the recirculating water to return to the tank, the master mixing valve only allows 10 to 30% of the water to return to the water heater. The balance is made up with cold water. So, the MMV allows for higher temperatures at the top of the tank and lower temperatures at the bottom of the tank, thus improving stratification. Master mixing valves can also tightly control the distribution system temperature. Modern MMVs have digital controllers in dead bands around 3 degrees Fahrenheit.
Recirculation pumps are a significant electrical load on the water heating system. They are typically oversized, which means both that there's typically too high of a flow rate of water running through the recirculation pump, and that there's too much energy being consumed by the pump itself. Electrically commutated motors offer advanced speed control and offer return temperature control, which allows for less electrical energy to be consumed. Demand controls offer electric savings at the pump, basically by turning the pump off when it doesn't need to be run. ECM pumps are more efficient and use less electricity than conventional recirculation pumps. ECM pumps can run at variable speeds, which means that they are more controllable than recirculation pumps. ECM pumps are also more expensive at first cost, but don't break down as often as recirculation pumps. Overall, they can be less expensive to operate over time because they use less electricity and they don't need to be replaced as often. This table compares the electricity usage and operating cost of 3 different pump configurations. The first is a 1/6 horsepower, 3-speed conventional recirculation pump running at its lowest speed. The second is a 1/8 horsepower ECM pump running in constant temperature control mode. And the last one is a 1/6 horsepower conventional pump controlled by a demand controller. The average power of the pump with demand control and the uncontrolled conventional pump is 150 watts compared to the 12 watts at the ECM pump, which means that there are significant demand reduction savings available from ECM pumps. All 3 pumps produce roughly the same maximum head, and the controlled conventional pump and the ECM pump use roughly the same amount of annual energy. In the annual maintenance cost column, it is assumed that the conventional pump is going to use $100 in maintenance costs per year. All of this leads to the last column, the 15-year cost, being $10,000 for the uncontrolled conventional pump and $3,000 for the ECM pump controlled by a constant temperature controller, and $3,900 for the conventional pump controlled with a demand controller. The clear winner is the ECM pump in constant temperature mode because it is less costly to run over time than the conventional pump, even when it's controlled with a demand controller.
Section 3. Water heaters.
The first step in selecting a water heater for a commercial food service facility, once the rest of the system is designed, is to select the kind of water heater that is desired. The most common water heater type is the standard efficiency natural gas fed storage water heater. The pros of this are that these heaters are very simple, they're robust, they're low cost, they're easy to specify, easy to fix, easy to replace, and relatively cheap with an upfront cost of between $2,000 and $9,000 depending on the size of the heater and how much storage it has. The cons are that it only has an 80% thermal efficiency. They can have significant standby losses. They can run out of hot water, especially if they're undersized, and they have a short lifespan in commercial kitchen environments, around 5 years. Condensing water heaters are more efficient than standard storage water heaters. They work by running extra lengths of exhaust through the water tank. This cools the exhaust and allows the water in the combustion exhaust to condense, which provides more heat to the water in the tank. The pros are that these heaters boast a 95% efficiency. They can have a much smaller standby loss because they're usually insulated. There's potentially a lower cost of install because sometimes these heaters can be installed with a PVC exhaust instead of standard ducting. And these pair very well with master mixing valves and demand recirculation controllers because their condensing function requires tank stratification to work. The cons are that these are more complex, which means that they're harder to work on. When installing these water heaters, you have to manage the condensate. The condensate produced by these water heaters is usually fairly acidic, and so there needs to be some kind of buffer installed on the condensate drain or a condensate drain installed in the floor to handle that. These are not the standard, and so less plumbers can work on these. They have a higher first cost, so when they run out of water, they cost more to replace. And like other water heaters, they have a relatively short lifespan in certain commercial kitchen environments, especially ones where they run out of water often. Tankless water heaters have become much more popular in smaller commercial food service facilities over the course of the last 10 to 15 years. They're sought after because of their smaller footprint and because outside installations are possible, which frees up space in the facility. These units also boast that they don't have a standby loss because they don't store hot water. The cons are that they have a significant pressure drop. These water heaters have a control system which allows them to limit the outlet flow of hot water so that they can meet their temperature set point. If multiple large points of use are run at the same time, these units will starve the entire hot water system, which can lead to critical hot water failures. There are minimum water flow limits on these as well, so if the demand is small enough, they will just send cold water in the hot water outlet pipe. To reach a facility's demand, the facility probably will need several units. These tankless heaters also have much higher gas input rates, which leads to higher installation costs by running larger diameter gas piping. Increased maintenance is required for these heaters in commercial food service facilities. Electric resistance water heaters are not very common in the commercial food service industry. The pros of these units are that they are zero net carbon and decarbonization friendly because they only use electricity. They are also simple and easy to work on. The cons are that they have a large amperage draw, which would require a relatively large service panel for commercial kitchen-sized loads. This would also lead to significant energy use with a more expensive fuel. That means that these heaters are much more expensive to run than ones fed with natural gas of similar size. Finally, there isn't a huge thermal efficiency gain over gas water heaters. Gas storage water heaters have thermal efficiencies around 80%, and electric resistance storage water heaters have efficiencies around 90 to 95%. So the energy efficiency gain isn't enough to offset the big increase in fuel cost. If California continues to decarbonize, heat pump water heaters are likely to become the most common type of water heater in commercial food service facilities. Heat pump water heaters boast a coefficient of performance as opposed to a thermal efficiency. They siphon energy from the air in their surroundings to heat water. An electric heat pump water heater with a COP of 2.5 would produce 2.5 kilowatt hours of useful water heating for every kilowatt hour consumed at the wall. This would provide very large energy savings over conventional gas water heaters and could, in some cases, be enough to offset the higher fuel cost. Heat pump water heaters can be packaged or split, which refers to whether the evaporator is connected to the hot water tank or remote. If the evaporator is placed in a hot room in the facility, the heat pump can provide some free cooling as an added benefit. The cons are that these units require large volumes of hot water storage to compensate for their slower recovery, which means that they require a larger footprint. Heat pump water heaters also require ventilation and have about twice the upfront cost of traditional water heaters, so there are significant barriers to their widespread adoption in the commercial food service industry without some level of incentivization. Electric heat pump water heaters are essentially a refrigerator. Energy is siphoned from the ambient space by use of an evaporator, which heats up a refrigerant fluid. This fluid then goes through a compressor and a condenser. The heat is deposited via the condenser into the hot water, and then the refrigerant is passed through an expansion valve towards the evaporator. The size of the compressor determines the maximum rate of hot water generation. Many electric heat pump water heaters have an auxiliary electric resistance heater, which essentially acts as a backup in case the heat pump can't deliver enough hot water to meet the load. Hybrid integrated storage water heaters have an evaporator, a condenser, an electric backup heater, and a hot water tank all located in the same chassis. They can be installed inside, which can provide energy savings. They can also be installed with additional hot water storage tanks to increase their capacities. Heat pump water heaters have a limited recovery rate compared to a conventional water heater. This requires a sizing adjustment when specifying heat pump water heaters to ensure that the highest hot water demand during the day can be handled without depleting the tanks. The larger storage volume also ensures higher operating efficiencies by minimizing heating cycles and the ability to heat a larger volume of lower temperature water depending on the location of the temperature sensor and set point. Split systems are generally more efficient with operating COPs ranging from 2 to 4. They can take advantage of single-pass heating, where cold water just goes through the heater one time, which preserves efficiency. Some package systems use multi-pass heating, where the water is passed through the heater multiple times before reaching its set point. Some systems are designed with swing tanks, which act as auxiliary hot water storage but can provide some additional heat for temperature maintenance. They can help to protect the heat pump water heater from having to handle recirculation losses, which can preserve its COP. One new technology is a heat pump assist, where a conventional gas-fired water heater is installed downstream from the heat pump. The heat pump then acts as a sort of water preheater, thus reducing the overall gas load. The benefit of this system is that instead of using an electric heater for the backup heat, gas is used. This system would be more robust to demand surge pricing because it could rely on gas during peak demand periods, but could also take advantage of the heat pump's COP. Finally, there are gas-fed heat pump water heaters on the market. These typically have COPs around 1.5. Generally, they are very expensive in first costs, and because of their relatively low energy savings, they offer very long payback times. Sizing a heat pump water heater is fairly nuanced. If the heat pump water heater is too small, it will provide limited energy savings and will rely mostly on its backup heater. If it's too large, it will never realize the full COP because it will be short cycling. The cost of a heat pump water heater scales with its size, so reducing hot water demand will decrease first cost by reducing the needed size of the heat pump water heater. Sizing a heat pump water heater to meet 30 to 60% of the peak load may be optimal for most full-service restaurants, but this comes with the caveat that enough storage needs to be installed at the site to handle those larger loads.
One concern raised There are a few design constraints for heat pump water heaters. One concern raised is the noise from running the compressor. Heat pumps usually run about 60 decibels. For reference, the noise level of ambient conversation in a restaurant is rated around 70 decibels. Vibration is also an issue, and space is an issue. Heat pump water heaters require large storage tanks. Both of these issues can be skirted by installing the heat pump and its storage tanks outside or on a rooftop. For heat pumps that need to be placed inside, small enclosed spaces are usually not suitable. The heat pump works by removing heat from the ambient air, so if the volume of air is limited, the temperature of the air will drop. If it drops too low, there won't be a heat source for the heat pump to draw from, and its COP will be compromised. This is also a concern for installing heat pumps outdoors in colder climates. Heat pumps that are installed inside restaurants also need to have frequent air filter changeouts to account for grease-laden air. Of particular concern for retrofits is that heat pumps require substantial electricity, which can require a panel or utility service upgrade in some cases. Many restaurants have limited available electrical capacity, so this is of particular concern to the commercial food service industry. The largest issue with heat pump water heaters is that the health department currently forces restaurants to size heat pumps by their input capacities as opposed to their output capacities. Traditional sizing guidelines effectively don't allow heat pumps to take advantage of their coefficients of performance, which leads to heat pumps being oversized by as much as a factor of 4. This is untenable for most food service operators because of first costs.
Water heaters are traditionally sized by adding up the flow rates or effective first hour ratings from each fixture on a hot water system, then finding the water heater's required minimum energy input rate to feed these fixtures.
These formulae are published by the health department. The first formula shows how designers are supposed to size gas water heaters. The minimum input is equal to the recovery rating times the temperature rise times the density of water times the thermal efficiency of the water heater. The recovery rating is a measure of how fast the water heater needs to be able to recover hot water after depleting its tank. The recovery rating is calculated based on the fixtures installed on the hot water system. A sample calculation is provided on the next slide. The second formula is for sizing electric water heaters and is essentially the same as the first formula except multiplied by a conversion factor to convert BTU per hour to kilowatts. This formula would need to change for heat pump water heaters to be accepted by the health department. Ultimately, the left side of the equation would need to read kW output as opposed to kW input, and the thermal efficiency would need to be changed to thermal efficiency or coefficient of performance.
This table provides the effective flow rate and recovery rates for fixtures commonly found in the commercial food service industry. The first column shows the flow rate that a tankless water heater would have to provide to feed the fixture. The second column shows the recovery rate that a tank-type water heater would have to provide to feed the fixture.
This formula shows how the health department calculates hot water demand for dish machines. The GPM demand is set equal to the quantity of hot water required during the rinse cycle as per the manufacturer's specification sheet, divided by the rinse cycle time, also taken from the spec sheet.
This table shows a sample water heater sizing exercise for a small quick service restaurant, a medium quick service restaurant, a small full service restaurant, and a large full service restaurant who all seek to use a tank type water heater. It shows the recovery rates from fixtures installed on each system and the minimum total recovery rates and minimum energy rates. It compares the minimum energy input rates from gas, conventional electric, and heat pump water heaters. It compares heat pump water heaters sized using 98% thermal efficiency to heat pump water heaters with an assumed 2.5 COP. This is done because currently health departments don't allow heat pumps to be sized according to their COPs. So this allows us to compare current accepted sizing guidelines to a more realistic engineered approach. Of particular note is that the minimum energy input rate required from the heat pump sized per health department guidelines is identical to the input rate required for a conventional electric resistance water heater. The sizing guidelines effectively force the designer to size a heat pump water heater by its resistance backup heater as opposed to its heat pump component. This forces heat pump water heaters to be oversized by a factor of 3 or 4, which means that the heat pumps would almost always be short cycling, which would never allow operation at the heat pump's designed COP.
Another issue with the traditional sizing method is that it effectively sizes tankless water heaters on the assumption that every fixture will be running at full flow rate at the same time. Tank-type heaters are effectively sized on the assumption that the hot water storage is depleted in the first hour, and then in the second hour, the restaurant is hit with another peak of 100% draw. Data from field monitoring studies shows that this virtually never happens in practice, and a real maximum second hour peak is about 30% of the first hour peak. This also fails to take into account that most of a facility's large draws, such as the dish machine fill or facility washdown, happen outside of service periods and usually only happen once per day. Traditional sizing leads to oversized water heaters and oversized distribution systems. Not only does this cause energy waste throughout the distribution system, but it decreases the operating efficiency of all types of water heaters. Traditional sizing also fails to account for the role of hot water storage capacity. A slow recovery rate can be compensated for with large storage, especially in commercial food service. Restaurants typically have 1 to 2 periods throughout the day when a large volume of hot water is used, but they have many periods throughout the day when hot water isn't needed at all, such as between meal rushes and overnight. If a restaurant had adequate storage and a water heater that could keep up with the total daily load as opposed to the maximum 1 hour load or the maximum instantaneous load, the facility's hot water needs could be met with a much smaller water heater.
One of the benefits of right-sizing a heat pump water heater is that a less expensive water heater can be selected. The cost of the heat pump scales with its size, so simply sizing a heat pump on its heat output can dramatically reduce the upfront cost of the heat pump water heater. This also means that the water heater would have a smaller electric input rate, which would lower the probability that a panel or service entrance upgrade would be required in a retrofit situation. A smaller heat pump would also have an easier time achieving its designed coefficient of performance. The ideal operating scenario for a heat pump water heater would be to essentially run 24/7, so a somewhat undersized heat pump with a small backup or swing tank in conjunction with a large primary storage tank is likely the most efficient configuration for most restaurants. Sizing tools for heat pump water heaters are available through Ecotope, an energy consultant based in Washington State. The calculator is set up for the residential sector, but a tool like this should be developed for the commercial food service industry. A heat pump assist configuration could be a good medium-term solution which would allay health department concerns about heat pump water heaters while still allowing restaurants to see the benefits of a heat pump water heater. Heat pump assist uses the heat pump for primary water heating, but it uses a natural gas water heater in place of a swing tank. The natural gas water heater can be sized to feed the hot water system on its own. Storage capacity is preserved with a large storage tank and a master mixing valve. A benefit of this system would be that it has a lower total amperage than an electric resistance backup and could be used to shave peaks during demand surge pricing times. This kind of system has not yet been installed in a commercial food service facility, but there is current work being done to show this concept. This table compares the energy use and operating costs of different kinds of water heaters in a full-service restaurant context. The daily operating efficiency takes idle losses into account from each heater. The gas heater has an effective daily operating efficiency of 70%, and even the most efficient single-pass electric heat pump only has a COP of 4.3. The most energy-intensive water heater is the conventional efficiency gas heater. The high-efficiency gas and low-efficiency electric heaters use almost the same amount of energy, and the heat pump uses the smallest amount of energy. The most cost-effective water heater is the gas pump in terms of operating costs, but this table also shows that a very efficient heat pump has a lower operating cost than the conventional gas water heater. This table also highlights the problem with conventional electric resistance heaters. They use less energy than conventional efficiency gas water heaters, but they can be between 4 and 5 times as expensive to operate. This cost difference is the main motivation to use heat pumps as the decarbonizing technology for hot water systems.
Section 4. Design Examples.
The first design example is for a quick service restaurant. This fictitious restaurant uses 350 gallons of hot water per day and requires 54 gallons per hour of recovery. It doesn't have a dish machine because it relies mostly on takeout, and the water heater is installed in the back room. The only difference in the design example for the quick service restaurant is the water heater, because the fixtures and hot water consumption are left constant. The first water heater in this example is the standard gas-fired water heater with 80% thermal efficiency. Its operating efficiency is 68%, which takes both tank idle losses and distribution losses into account. It is the most energy-intensive option, with almost 100,000 kBTUs of energy per year. The second water heater is a condensing water heater. It has an operating efficiency of 84% due to its condensing function and uses around 80,000 kBTUs of energy per year. This shows that there are substantial energy savings for quick service restaurants just from retrofitting the water heater to a condensing water heater. The third water heater is a gas-fired heat pump with a standard backup tank-type water heater. It has an effective operating COP of 1.4. This system uses both gas and electricity. To calculate the annual source energy, the electricity use was converted from kWh to kBTUs, and this example clocked in around 54,000 kBTUs per year. The next water heaters considered were an electric resistance water heater and a hybrid heat pump with electric backup heat. The electric resistance water heater had the highest annual source energy of any water heater considered after correcting for grid transmission losses. The heat pump used just over a quarter of the energy used by the electric resistance heater. The last water heaters considered were electric heat pump split systems with electric resistance backups. The first is a heat pump with a low GWP refrigerant with a COP of 4.7, and the second is a heat pump with a CO2 refrigerant and a more efficient compressor with a COP of 5.5. The effective COPs are 3.7 and 4.5 respectively, which account for short cycling and the use of electric resistance backup as well as system losses. These water heaters have the smallest annual source energy of any water heater considered in this design example. This table considers the cost impacts of these different water heaters on the quick service restaurant. It shows the first year energy cost, the first year water cost, the total installed cost, the 1-year cost, payback period, 10-year cost, and percentage increase in 10-year cost of each of these types of water heaters. Unsurprisingly, the condensing gas-fired water heater was the lowest 10-year cost of any water heater considered. However, the electric heat pump split systems only added between 15.4 and 22.8% to the total 10-year cost on top of the standard gas-fired water heater. For the full-service restaurant, there were many design constraints that could have been considered. For this design example, the full-service restaurant has a pre-rinse spray valve in a dedicated dish room, uses a door-type dish machine in that dedicated dish room, and has a separate bar area and multiple utility and compartment sinks found throughout the restaurant. In this design example, we will consider impacts of more efficient fixtures as well as the impacts of different water heating mechanisms for the design. Lastly, it will consider different distribution strategies such as continuous recirculation and distributed generation and see the energy impacts of that on the overall system energy usage and cost. For the full-service restaurant, the throughput was taken to be constant. This full-service restaurant washes 250 racks of dishes per day. For fixtures, the impact of the dish machine and pre-rinse spray valve were considered. A standard efficiency high-temperature dish machine was compared to a heat recovery door-type dish machine with cold feed only. A pre-rinse spray valve at 1.2 GPM was compared to a 0.7 GPM model. For the distribution system, continuous recirculation was compared to a recirculation system controlled by an electric commutated motor in constant temperature mode. This was compared to a distributed generation system where the front-of-house bar was fed with an electric point-of-use water heater and the main recirculation loop was controlled with an ECM. The impact of pipe insulation was considered. Many water heaters were considered. A standard efficiency gas water heater, a condensing water heater, an electric heat pump assist with a condensing water heater, a gas heat pump assist with a condensing water heater backup, a hybrid heat pump with electric resistance backup, and a single pass heat pump with an electric swing tank were all considered in this design example. This next section will consider the impact of different gas water heaters on the full-service restaurant. The first system considered is the business-as-usual case. It uses a 70% thermal efficiency storage water heater set at 145 degrees Fahrenheit. This is done so that it can deliver 140 degrees Fahrenheit to the high temperature door type dish machine after all of the distribution system losses. This system uses continuous recirculation with a standard efficiency pump. It has pipe insulation on straight distribution pipe only, and it uses an Energy Star rated high temperature door type dish machine without heat recovery. The second system has many of the same fixtures as the first system. However, there are some fixture improvements. The second system has a digital master mixing valve, has an upgraded high efficiency pre-rinse spray valve, an ECM pump, additional pipe insulation, and reduced distribution supply temp to 142 degrees Fahrenheit. This was done because the added pipe insulation and the ECM pump managed to reduce the overall distribution system losses. System 3 is the addition of a heat recovery dish machine with cold feed only. It drops the operating temperature of the hot water system to 122 degrees Fahrenheit, and it improves the efficiency of the water heater to 90 degrees because it helps to preserve tank stratification. Systems 4 and 5 used the most efficient combination of fixtures, but fed them with a gas-fired domestic hot water system with an electric heat pump assist. The first three systems used different combinations of fixtures and therefore had different water usages. In the first system, the least efficient dish machine and least efficient pre-rinse spray valve were used, leading to the highest total amount of hot water usage at 847 gallons per day. The second system uses the upgraded pre-rinse spray valve, which dropped the pre-rinse spray valve water usage from 108 gallons per day to 72 gallons per day. The third system used the high-efficiency dish machine with heat recovery, which dropped the dish machine's water usage from 339 gallons per day to 176 gallons per day, and the total hot water usage from 811 gallons per day to 472 gallons per day. Systems number 3, 4, and 5 used the same combination of fixtures and therefore had the same hot water usage per day. This table compares the energy usage of the full-service restaurant hot water systems. The recirculation pipe heat loss was lowest in the third, fourth, and fifth systems because they had the best controlled recirculation system and the lowest distribution system operating temperature. The third through fifth systems also had the lowest hot water load because they used the heat recovery dish machine. The heat recovery dish machine was responsible for significant energy savings both at the water heater and on the distribution system. The heat pump systems had the lowest gas usage between only 3 and 5 therms per day. The total electricity use row includes the electricity use of the dish machine. The electricity use of the standard dish machine was almost the same as the electricity use of the heat recovery machine. The fourth system had the lowest annual source energy of any of these systems. This table compares the operating costs, installation costs, and total system lifetime costs of the 5 systems compared in this design example. The conventional system had the lowest total installed cost but the highest operating costs. This meant that each of the other systems had a positive simple payback time. The most cost-effective system was system number 3 with the addition of the heat recovery dish machine. However, system number 4 relied much more on electric energy and only used about $8,000 more than system number 3. This shows that it is economically feasible to decarbonize similarly sized full-service restaurants. Additionally, if electric rates were to stop increasing faster than gas rates, the 10-year total costs of these systems could be different, leading to a faster payback and more attractive total system cost for the decarbonized system. This next section will consider the impact of different electric water heaters on the full-service restaurant. For the next set of design examples, the most efficient fixtures and distribution system were used, and only the water heater was changed. Each of the systems had a heat recovery dish machine, a low-flow pre-rinse spray valve, and a distribution system controlled by an ECM in constant temperature mode operating at 122 degrees Fahrenheit. Both the hot water load and the energy load were the same for all of the systems. The first water heater considered was a packaged hybrid heat pump and electric resistance water heater. To meet the load, three 120-gallon units are needed in parallel. This design example used the Health Department sizing guidelines. An effective COP of 2.5 was used. The most efficient water heater used in this design example was a single-pass heat pump with an electric swing tank. The conventional Health Department sizing was compared against an engineered sizing. The conventional Health Department sizing used a swing tank design with 4 small split single-pass heat pumps placed in the exterior and connected to 2 119-gallon storage tanks and a 30-kilowatt 112-gallon electric resistance water heater. The heat pumps were modeled to meet all the hot water draw loads and 50% of the recirculation reheat load. The engineered sizing used a design based on the hot water output of the heat pumps. It used 6 small split heat pumps connected to 2 storage tanks and a much smaller 3.4 kilowatt electric resistance backup water heater. This table compares the operating and installed costs of the heat pump water heater systems. The payback periods are compared to the conventional gas-fired water heater. These payback periods are somewhat higher than the payback periods for the gas-fed systems, making them less attractive in general. The lowest payback time for the gas systems was 1.1 years, and the lowest 10-year total cost was $315,000. This table shows that the single-pass heat pump with the plumbing engineer sizing and the hybrid heat pump and electric resistance systems are both reasonably economically viable, but electricity costs would need to come down before they would be competitive with the lowest gas system. Our final design example considers the impact of distributed generation on the cost of each system. It ultimately uses a small controlled recirculation loop and remotes out many of the hot water loads with small point-of-use electric resistance heaters. This design reduces recirculation losses and can help to preserve the operating COP of the water heater. This table compares a fully distributed generation system with an electric heat pump water heater to the lowest cost gas-fired system from the first full-service restaurant design example. The heat pump water heater example uses 2 5.5 COP electric heat pumps, a 119-gallon storage tank, a backup electric resistance water heater at 18 kilowatts, and 10 point-of-use heaters at the lavatory sinks and at the bar. The heat pump has a recirculation loop controlled with a demand recirculation controller and has an operating COP of 4.3. It uses an annual source energy of 583,000 kBTU. Overall, the heat pump system is fairly competitive with the high-efficiency gas system, only using about $600 more in utility costs per year. Even with the increased cost of the equipment, this shows that with clever system engineering and proper sizing, heat pump water heaters are a viable technology for the commercial food service industry.
This table shows the best paybacks from the full-service restaurant design example. The best simple payback time and the lowest 10-year total cost was the gas-fired DHW system with recirculation control, a heat recovery dish machine, and a condensing water heater. For the all-electric water heating systems, the fully distributed generation heat pump water heater system boasted a 1.3-year payback and a comparable 10-year total cost to the condensing system. The single-pass centralized system also had a 4.3-year payback over a conventional system. All 3 of the best payback systems relied on a heat recovery dish machine and high-efficiency fixtures for a better designed system with lower hot water demand of the water heater. Heat recovery dish machines effectively opened the door for heat pump water heaters to be cost-effective, and as California decarbonizes, heat recovery dish machines and heat pump water heaters need to be installed at more restaurants. Some cost savings will be left on the table, but there will still be significant savings on the order of $10,000 per year over the conventional systems. Electric resistance water heaters are simply not efficient enough to offset the higher fuel costs, but these design examples show that with system design best practices in heat pump water heaters, savings can be achieved through decarbonization. Key takeaways. Fixtures. The easiest way to achieve an energy-efficient hot water system in a commercial food service facility is to start by specifying efficient fixtures and equipment. The designer should design a hot water system by specifying the equipment first, then specifying the distribution system, and then finally working back to the water heater. This will allow the designer to have an accurate idea of the hot water demand and the energy usage that the hot water system is going to require, which will allow them to accurately size the water heater. This will allow the water heater to operate at its optimum efficiency most of the time. Some best practices for specifying fixtures are to specify high-performance pre-rinse spray valves rated at below 0.8 GPM, to specify ultra-low flow aerators on hand sinks at 0.5 GPM or below, and to select a commercial grade point of use heater at hand sinks if possible. Finally, the designer should specify an ENERGY STAR certified or better dish machine with heat recovery and only cold water supply connections. These last two steps are of critical importance because they will dramatically reduce the hot water demand seen by the water heater in the mechanical room. Especially specifying a heat recovery dish machine can reduce the overall facility hot water demand that the water heater sees by up to 50%. Key takeaways: distribution and water heaters. Position the water heater as close to the dish room and other sanitation sinks as possible. This will reduce the total amount of hot water piping and reduce heat loss through the distribution system. If specifying a gas-fired water heater, specify a high-efficiency condensing water heater with or without heat pump assist. This will allow the water heater to operate at a higher efficiency than if specifying a conventional efficiency water heater. If specifying an electric water heater, specify a hybrid heat pump / electric resistance storage water heater or a single pass split heat pump storage tank primary water heater with an upper element. Specify distributed generation where possible, because this will further reduce pipe heat loss. Finally, install electrically commutated motor pumps with constant temperature control for continuous recirculation systems. This will further reduce the amount of recirculation and pipe heat losses through the system and increase the overall energy efficiency of the system. Thank you for listening to this presentation. For more information on designing efficient hot water systems for the commercial food service industry, please refer to the design guide, which is accessible at the link at the top of this presentation. For information on operating an efficient hot water system in the commercial food service industry, please refer to the companion design guide or the companion presentation. For more information than is contained in any of these resources, please feel free to reach out to Amin Dalaga or Michael Slater, who are both accessible at the email addresses listed on this slide. Thanks again.